Okay, so the problem we're dealing with, we have a contest to see how many jelly beans are in a jar. And the hint they give us is the jelly beans, when evenly divided by either 2, 3, 4, 5, 6, 7, or 8, we always have one jelly bean left over, or a remainder of 1. So let's switch over and write a program to take care of this. We're going to set up a loop to check each one of these, and essentially I'm going to go through and kind of do a brute force method again, check each number along the way to see what number, when we check it against all these numbers for divisibility, to see which one has a remainder of 1 for all of them. So let's start out. I'm going to create a Boolean value, is not done. This is going to control my loop, and I'm going to initially set it to true. And so is not done means what? Keep processing the loop. I need a value that we're going to keep checking, and I'm just going to initialize it to or create an I variable initialized to 8. The reason I picked 8 is we know the number is not going to be less than 8 because even if we have 8, there's supposed to be 1 left over. So I'm going to go ahead and start with 8, and we'll set up our loop. So we're going to do a while loop, and again we're going to do while we're not through. So I'm just going to say is not done here. Okay, and a lot of times with a condition in a while or an if, you normally see the comparison operators here. But when you make a comparison, you end up with a result of a Boolean value. And so in this case, I already have a Boolean value. This is already going to be true, so I don't really need to compare it. I could compare it to true, but I don't need to. Okay, so I'm just going to say while we're not done, keep processing. Okay, and so this will be my loop. And of course, I need to increment the value of I within the loop. And then at the end of the loop, I'm going to go ahead and output. Once I find the right value of I, we'll just go ahead and say, hey, I is the answer we're looking for. Okay, and that'll be that. So we need to go back in here and make sure we increment I in the loop. Otherwise, we end up with the famous infinite loop. So we'll do I++ here. That'll take care of that. Okay, so now we have to put our conditions in to say, hey, what if our original, number is not what we're looking for? So we're going to have to do, we'll go ahead and assume that we got it, right? So we're going to say is not done is false, assuming that we ended up with the right answer, and then we're going to try to disprove that during the loop. Okay, so we're going to check those numbers 2 through 8 to see if any of those will invalidate our claim that we are done. Okay, and then if we are done and none of our other checks check out, then we'll exit the loop. Okay, so let's check to validate. We'll say if, and we'll take our first number 2. So we'll do I, and again we're looking for a remainder of 1. So remember the mod operator, or which is the percent sign. So I mod 2, and if that's not equal to 1, we have a problem, because for each number 2 through 8, if we have the number we're looking for, we're supposed to have a remainder of 1. Okay, so if we don't have a remainder of 1, we're going to say is not done. Well, we're not done yet, right? So that's equal to true. Okay, and so if we check that one out and we divide by 2, we don't have a remainder of 1. Hey, we're not done. Okay, so our original assumption at the top of the loop that we're done is not right, so we'll have to continue. Now we need to add our other checks in here. So mod 2, we need to do the same thing for 3, 4, 5, 6, 7, and 8. And so we're going to check each one, and as long as we don't meet the requirement of having a remainder of 1 when we divide by each one of these numbers, we're going to assume we didn't get it right. So let's check this out and see if it actually gives us something that we're looking for. We'll compile and run this. And it gives us 841 as our answer. So looks like we got 841 jelly beans in the jar. So that worked pretty well. Kind of a brute force, and it didn't take very long for it to run once we have the code set up. Now if we look at this, you kind of see a lot of repetition. There's these if statements are kind of repeated, except for we've got one minor thing changing, 2, 3, 4, 5. So we can probably do this a little bit more efficient way. So I'm just going to get rid of all the repetitive if statements for 3, 4, and we're going to replace that a little bit more efficient way. So what we're going to do is go through here and set up a loop, and so we're going to do a for loop, and we're going to go from 2 to 8. So I'm going to initialize, and I'm just going to use my counter as j. So I'm going to set j equal to 2, and then we'll know when to stop when j is, as long as j is less than or equal to 8. So that's where we'll stop, at the 8, and of course we're going to get there by 1, so j++. That sets up our loop, and this will be our loop. The only thing we need to change for this to go from 2 to 8 here is, instead of the constant value 2 for this first if, we're going to change that to j. And so now we've got that little bit, more compact looking code using this loop. And because it's considered one statement after that for, we don't really need braces. You could add those if you want. But let's try this out and see if this version with the loop is still working. So we'll compile and run that. And it works out. We get the same answer. Just a little bit simpler code. Well, maybe not simpler, but more concise. And we don't have a lot of repetition. Okay. So that was a programmatic way of doing it, and we could have approached the problem a little bit different way, maybe a little less fun than programming, but we can look at our original problem. We can solve it using a least common multiple method. And so if we're looking at the values 2, 3, 4, 5, 6, 7, and 8, we can find the least common multiple, and that'll get us pretty close to our answer because we're going to have a remainder of 1. So what we're looking for is what number is the least common multiple of these. So to do that, we need to do prime factorization. So 2 is actually prime, so we will include that in multiplying these numbers together to get the least common multiple. 3 is also prime, so that's good. 4 now has 2 prime factors, which is just 2 times 2. So we only need 1 2, right? So we've got 2 2's here, so we'll just go ahead and eliminate that first 2, and we'll include 4 that has 2, which is 2 times 2. Okay, we don't need 2 because we already have a 2 here in the 2 times 2. 5 is prime, so we'll include that. 6 has 2 prime factors, but it's 2 times 3. Well, we already have a 3, so we don't need a 3, and we already have 2 2's, so we don't need another 2. Okay, so we can eliminate 6. 7 is prime, so we need 7. And 8 has prime factorization of 2 times 2 times 2, so 3 2's. So this one with only 2 2's, we don't need it. Okay, and so what we do to find the least common multiple now that we've eliminated is take 3, the ones left over that we haven't underlined, so 3 times 5 times 7 times 8, and that's going to be equal to 840, which is the least common multiple. Now if we want a remainder of 1, we just add 1 to it, right? So if they're all multiples of 840 or factors of 840, we multiply those together, 841 would give us a remainder of 1. Okay, so that's a little bit different way we could have done it. But I kind of like the programmatic approach. we can go back to that and say we want to do the same thing for a different number. We could let's say 10, and that to 10 as well. Okay, and let's execute this and see what we get for the numbers 2 through 10. And so for that we get 2,521. So I like writing programs to do this kind of stuff, because with some minor modifications you can solve a different problem pretty quickly without going through a lot of trouble. But it just goes to show you it's probably good to know a little bit of math too, that you can incorporate in some of these problems. So hopefully this was helpful, and I'll see you next time.